and welcome. In this lecture video, we are going to look at how to use indefinite integrals to derive equations of motion for one-dimensional motion. And these are largely called a class of problems called initial value problems. All right. So here I have a non-constant acceleration. It depends on time. And I have two initial values. All right. So over here on the right-hand side, that's what these guys are. I have my velocity at time 0 is 2 meters per second, and my position at time 0 is at the origin at 0 meters. We're going to be using those to evaluate that pesky constant of integration that we get when we take an indefinite integral. All right, so we are going to go ahead and say that the integral of the acceleration is equal to the velocity. Now, why is that true? Because remember that the derivative of velocity is acceleration, and the integral involves taking the antiderivative. So if we take the antiderivative of the acceleration, we should get the velocity function, and indeed we do. All right, so we are going to go ahead and take the antiderivative of the acceleration function, and we are going to be taking that derivative with respect to the variable t. Don't freak out about this dt. It's just there for right now to tell us what we're integrating with respect to. Time is my variable. All right, so again, this is t to the first using the power rule. We increase that by 1, so we have t squared when we take the integral, and we divide the coefficient by the new exponent, and we get 1. So we have 1t squared, and there's the pesky c. So this is an equation for the velocity of this particle at any time t. But we've got to solve for c. That's where the initial value comes in. All right, so the initial value gets plugged in. It's the velocity at time 0, and the velocity is 2 meters per second. So the velocity is 2 meters per second, and it's the velocity at time 0. So we have 1 times 0 squared plus c. Even I can do this algebra. C is equal to 2. So we can now get a complete function for the velocity at any time t. It's not just t squared. It's t squared plus 2. And so once again, I want to know what the velocity is at 1 second. We plug in 1. We've got the velocity at 1 second. I want to know what the velocity is at 256 seconds. We plug in t equals 256 and evaluate. Okay? Now, remember that the derivative of position gave us velocity. So if we take the antiderivative of velocity, we should get a function for the position. Let's see how that works. So there's our velocity function derived in the last part, and we're going to integrate the velocity function with respect to t, and that is going to give us our position function at any time t. So let's go ahead and do it. We're going to integrate t squared plus 2 with respect to t. And taking the antiderivative, we end up with, again, remember you add 1 to the exponent, so it's t cubed, and the coefficient gets divided by that new exponent. So a third t cubed plus, remember that's really t to the 0, and we add 1 to the exponent, we get t to the first, 2 divided by 1 is 2, and we get the pesky c. You've always got to put the c in there. So this is our position at any time t. Go back and remember that our initial condition was x at time 0 was equal to 0 meters. This thing starts its movement at the origin. Okay, I love these initial conditions because remember it's the position at time 0, that's the time, and then that's the position. So the position at time 0, 2 times 0 plus c. And we get goose eggs all around. So we get 0 is equal to our constant of integration. That's why I like that specific initial value. Okay, so if c is 0, we now have our position function at any time t. We have 1/3 t cubed plus 2t plus nothing. All right? So now I've got a position function, I've got a velocity function, I've got an acceleration function. Life is good. Now I'm going to show you something fun. We're going to start with a relatively uninteresting equation, a equals a. Acceleration equals acceleration. It's some constant acceleration. We don't know what it is, but who cares? Our initial conditions over here on the right, we have the velocity at time 0 is v sub 0, and the position at time 0 is x sub 0. Again, pretty uninteresting, pretty generic. Okay, let's derive the equations of motion with this. We take the integral of acceleration with respect to time, and we're going to get the velocity. Okay, Okay, so the integral of a with respect to time, that means there's a t to the 0 here. We're integrating with respect to time. We're integrating a constant. Remember, when you integrate a constant, you just get the constant times your variable. So this is going to be a t plus that pesky constant of integration. So here's our velocity function. Velocity is equal to at plus c. Here's where the initial condition comes in. Remember again, that's the time, that's the velocity. So v sub 0 is the velocity, and the time is 0. So we get our constant of integration is equal to v sub 0. So let's rewrite that equation. V, and let's go at any time t, is equal to a times t plus v sub 0. That should look really familiar to you physics students. Remember that class of equations that only works when the acceleration is constant? What did they call those? I can't remember. Well, let's keep going and see if the next equation looks familiar in case that one doesn't. So we're going to integrate the velocity with respect to time, and that's going to give us the position function. Right? So we're going to integrate that function we just came up with, at plus v naught, with respect to time. So let's see here. This is t to the first, right? So we get t squared, and we divide a by the new coefficient. I'm sorry, the new exponent, a over 2, plus v naught. That's a constant. Remember, the integral of any constant is the constant times your variable. So that's going to be v naught times t. We get that pesky constant of integration again. This is our position function. And again, we're going to plug in our initial conditions. There's the time, there's the position. So our position is x naught. Our time is 0. And again, our constant ends up being x sub 0, like it was in the last one, v sub 0. So finishing out our position function at any time t is equal to, let's write it this way, 1/2 at squared plus v naught times t plus x naught. Wow. If you didn't recognize the first one, you for sure should recognize the second one. Those are our kinematic equations. What's missing? The v squared one, because we can set those equal to each other. You know, solve this one for time, throw it into this one, and you'll get the v squared kinematic equation, right? So we can see how those kinematic equations are derived, starting with very, very, very simple conditions. And you don't even need to memorize them anymore. Start with a equals a and do a couple of integrals, right? So that's lovely. Now, my young physics students, you have the power. I give you a velocity function, and I say, give me the other two equations of motion. I want the position function, and I want the acceleration function at any time t. Acceleration function, oh man, piece of cake. We take the derivative with respect to t. We've got 6t. There's our acceleration function, right? We want to get the position function. We integrate. So our position function is the integral of the velocity, which is going to be t cubed. 3 over 3 is 1, plus the constant of integration there. And I gave some weird initial conditions just to show you that it doesn't have to be times 0 for this to work, right? So we use our initial conditions into that equation. We got the time is 2, the position is 4. So the position is 4, the time is 2, and we're solving for c. So we've got 4 is equal to 8 plus c. We've got -4 equals our constant of integration. Our position function then at any time t is going to be t cubed. Give me a t. T cubed plus, no, minus 4. Boom! Oh my gosh. You don't even recognize the power at your fingertips now for interpreting, evaluating, and describing one-dimensional motion. All right? So there you have it. That's all I got for you this time. Now it's time to practice.